In today's lecture, I'm going to discuss about electrodynamic wattmeter. So the electrodynamic meter movement mechanism is going to be used to implement a wattmeter. So the basic symbol of wattmeter is basically something like this. So you have used the wattmeter in different labs for in a power system or electrical machine courses. You have used the wattmeter to measure power. So the general symbol for the wattmeter is something like this. So the wattmeter contains two separate coils. One is called the current coil, another one is called the pressure or the potential coil. So the current coil is basically connected along the load or in series with the load, and the pressure coil is connected in parallel with the load. So the current coil basically carries the current that is supposed to be flowing through the load, and the pressure coil, as it is in parallel with the load, so the voltage across the load is also the same as the voltage across the pressure coil. Now, as per the connection, the current coil is supposed to carry a little bit more current compared to the load, because the current that is passing through the current coil, let's say IC, it is going to be divided in the two branches. So let's say I, this is the current which is going to flow through the load, and this is the current which is going to flow through the potential coil. So but the current flowing through the potential coil is less compared to the overall current flowing through the current coil. So in a sense, it can be said that the current coil is carrying the uh, current which is actually supposed to flow through the load. So in that sense, it can be said that the pressure coil is sensing the current that is passing through the load, and the potential coil is sensing the voltage that is uh, passing that is present across the load. So in terms of the voltage and the current, the wattmeter can uh, uh, give the proper deflection needed to measure the power in watts. Now, the two circuits shown over here in figure A and B, the connection of the fixed coils and the moving coils of an electrodynamic meter movement mechanism to implement a wattmeter is shown. Now, a simplified circuit representations are given over here. So let me say that for figure A, this is one of the fixed coils of the electrodynamic meter movement mechanism. This is another fixed coil of the electrodynamic meter movement mechanism that we discussed earlier. And this coil over here represents the moving coil. So as we're using the short forms, so FC indicates fixed coil and MC for moving coil. Now, one modification in this electrodynamic movement implementation mechanism is that in previous class, while discussing the electrodynamic meter movement mechanism, it was considered that the same winding or wire is used across the fixed coils and also through the moving coil. So both the fixed coils and the moving coils are carrying the same current. But in this case, in order to implement the wattmeter, there is slight variation. Here the two fixed coils are connected in series, and the fixed coils are connected sort of in series with the load. So the fixed coils are actually working as the current coil in case of the wattmeter. Now, how the moving coil is connected? One of the terminals of the moving coil may be connected at this point, at one of the terminals of along the node with where one of the terminals of the load is connected, and then the moving coil connection can be completed through a multiplier resistor R to the other terminal of the load. So the moving coil is here basically connected in parallel with the load. So the moving coil is going to work as the pressure coil or the potential coil of the wattmeter. So R over here is representing the multiplier resistor. So this multiplier resistor, as the function of multiplier resistor was discussed in case of voltmeters as well. So they allow to increase the range of operation for the meter. So by adding a multiplier resistor, large amount of voltage can be uh, uh, supplied across the potential coil. And another purpose of using the multiplier resistor is to, make this pressure coil branch or the moving coil branch as purely resistive as possible. So that is another purpose of using the multiplier resistor, because the coil winding is going to be basically having an inductive nature. So if some resistor is connected, so that resistor is going to allow the inductive behavior to be mitigated, and if the resistor value is increased, the branch will become as much uh, uh, purely resistive as possible, so that the uh, uh, I mean uh, the voltage and current through this branch doesn't have too much lagging in between them, or phase difference in between them. Now let's say these fixed coils, they are carrying a current IC. So the same current IC is going to flow through both the fixed coils. And at this point, or at this node, the current is going to be divided into two parts. One of the part, let's say, is going to flow through the load, that is represented here by I. And another portion of the current is going to flow through the moving coil, that may be represented as IV. So the current flowing through the fixed coils, or the current coil, is IV plus I, where capital I is the current flowing through the load, and here the capital E represents the voltage across the load. So using the wattmeter, the intention would be to measure the power in terms of the multiplication of E into I. Now figure B is actually showing a simpler representation of the wattmeter, sort of showing the connection in terms of the conventional symbol that we use while representing the wattmeter. So you can say that this coil over here is representing the series connection of the two fixed coils, and this coil over here is representing the moving coil. So instead of as both the fixed coils are connected in series, so in order to make the circuit representation simpler, the fixed coils are represented by a single coil over here, and the moving coil is connected in parallel with the load as before, along with the multiplier resistor R. Okay, now as discussed already, that IC is representing the current flowing through the current coil, which is the fixed coils here, IV current flowing through the potential coil, which is the moving coil in this case, and I is the current flowing through the load. Now the deflection theta that is going to take place due to the movement of the moving coil is supposed to be proportional to the product of the currents flowing through the fixed and moving coils. Because if we also try to concentrate on the discussion of the previous lecture, that the current that is supposed to be flowing through the fixed coils are going to produce the magnetic fields. So in presence of the magnetic field produced by the fixed coils, the moving coil is going to experience some force. So here the moving coil is carrying a separate current, which is represented as IV. So overall, as it was discussed in the previous lecture, that the torque developed in the moving coil is going to be proportional to the currents, product of the currents flowing through the fixed coils and the moving coils. So similarly, if the torque is proportional to the product of the currents flowing through the fixed coils and the moving coils, then the deflection resulted by the torque should also be proportional to the product of the currents flowing through the fixed and moving coils of the electrodynamic meter movement mechanism. Now, if the average deflection is considered over one time period, then it can be represented as theta equals k into 1 by t 0 to t ic into ip into dt. So the product of the two currents, okay, instead of ip, I should write here IV, because we're representing the current flowing through the moving coil by IV. So the average deflection can be considered to be in terms of the product of the two currents from the fixed through the fixed coil and the moving coil, integrating them within one time period and then dividing by the time period to take their average. In K is the constant, it can be said that it is the instrument constant. It might depend on the length of the windings, then the area of effective area of the windings, then the magnetic field that is produced. So this might depend on several factors. Now, for the time being, we are going to concentrate on the effect of the currents in producing the deflection. So if we further elaborate this integral portion, if we try to proceed along with the integration, then first of all we can rewrite it as k into 1 by t integration from 0 to t instead of ic. So ic is equal to iv plus I. So we can consider that iv is negligible because iv is very less than or compared to I, the current flowing through the load. So for that, we can assume that IC is almost equal to I. So here in this expression, then IC can be replaced with I and IV can be replaced with E divided by RP. Sorry, let me just write R. So as we have denoted the multiplier resistor by R into dt. So once we do so, let's say that the R is representing the resistance of the moving coil and also the multiplier resistor. So let's say we can take the R out of the integral operator because it is also a constant, so we can factor it out. Let's say then we can rewrite the constant to be K1 because we are taking the resistance outside. Then we can write 1 by t integration 0 to t I into E dt. So for this case, uh, uh, one more thing I can specify over here for clarity, that as we are taking the integration with respect to time, so instead of just representing I and e, I should represent them in terms of the function of time. That would be more logical thing to do. So let me do that first. So if I write I of t, e of t, that would be more logical in this case, because I'm taking the integral with respect to time, and if the signals are AC signals, they are supposed to vary with respect to time, so they should be written at this instant as a function of time. And we can say that k1 would be equal to k divided by r. So at this point, if we also look at the expression for average power, how we represent average power. So the formula for average power is if we represent it in terms of time period, then it would be 1 by t integral from 0 to t. It can be also said that it would be the product of the voltage and current, integrating them from the limit 0 to t and dividing them by the time period to take the average. So if we consider the general formula that is used to calculate average power, then from the expression of deflection we can see that this portion is actually same as the one we use to calculate the average power, just multiplied by a constant. So from this sense, it can be said that the deflection that is supposed to be obtained from the this electrodynamic meter moment mechanism, that can be used to measure the power of a load, or this movement can be used to form a wattmeter to measure the power. Okay, now let us try to look at this figure. So this is showing a relation between a voltage, the load voltage and the load current in terms of their phase difference phi. So it might happen that the voltage across the load and the current through the load are having some phase difference depending upon the type of load. What is the nature of the load? Whether it is resistive, inductive, or capacitive, or mixed. So depending upon the type of load, there might be phase difference, there might not be phase difference. So let's say if there is phase difference, let's say the voltage is leading the current by a phase angle of phi. So the for these cases where there is some phase angle, what the wattmeter should do, so the wattmeter should actually measure the power to be ei into cos phi. Okay, so it not be a simple relation like a resistive load where the voltage and current can be directly multiplied. So apart in case of any phase difference, the in phase component of the current should be considered. So if the current is along this direction with a phase angle of phi, so its corresponding in phase component would be I cos phi. So that should be multiplied with the voltage in order to obtain the overall power for that particular load. So now the wattmeter should be capable of measuring this quantity, or the deflection should be in proportion to this particular quantity. So now let us consider that the voltage across the load is represented by a sinusoidal signal considering time varying quantities, and let's say the current through the load may be represented as I sine omega t plus minus phi. So depending upon the type of load, it could be plus phi or minus phi. So let us keep it is in general. Now, following the expression of theta written in the previous slide, which was k1 into 1 by t integration 0 to t e of t multiplied by I of t into dt. Now here we can put these sinusoidal expressions of the voltage and current. So what would we have over here is e sine of omega t into I sine of omega t plus minus phi. Now here we can use the general trigonometric rules. Now first of all, we can factor out E and I. We can consider that the peak values are going to be fixed for a particular signal. So we can factor them out. We can write them as E into I divided by T into half of G0 to T. So we're just going to apply simple trigonometric rule of 2 sine A into sine B. So we have just factored out a 1 by half and this factor we have written. Now if we apply the rule of twice sine A into sine B, we can rewrite the sine omega t into sine omega t plus minus phi as cos phi minus cos twice omega t plus phi. After that, if we proceed with the integral, so a minus sign should prevail actually. So it should be minus cos phi into t minus sine twice omega t plus minus phi divided by twice omega and within the limit from 0 to t. Now if we actually further, I mean, elaborate this term over here, sine twice omega t plus minus phi, then we can actually rewrite it as the limit 0 to t. Now if we put the limit of 0 and t in these particular expressions, then we will see that uh, this overall term will actually give us 0 if we put the limit from 0 to t. Then with the other term, this one cos phi into t, we will be ending up with cos phi into capital T if we put the limit from 0 to t. So in that sense, if I rewrite this, okay, let me just rewrite it over here. If I rewrite this entire equation, that what I have left off with 1 by twice t ei into cos phi into t, sorry, capital P. So this t and this t will cancel out, so we will have k1 into ei divided by 2 cos phi, and furthermore we can rewrite it as ERMS IRMS into cos phi, just dividing this portion e by root 2 into I by root 2, so replacing them in terms of the RMS representation. So from this expression of theta over here, we can easily say that the theta is proportional to ERMS IRMS cos phi. So it is quite justifiable that even if there is phase difference between the voltage and current of the load, the wattmeter configuration using electrodynamic meter moment mechanism can be used to uh, measure power accordingly or as it is required. And as the relation is established in terms of RMS values, so the scale of the deflection can be also calibrated in terms of RMS values. And if the scale is calibrated in terms of RMS values, then the same scale can be used for both DC quantities and for AC quantities. Now at this point, we are going to discuss about the sources of error in case of wattmeter, and the sources of error can be in terms of the connection of the moving coils, where we are connecting the moving coil. Let's say if we are connecting the moving coil after finishing the connection of the fixed coils, then what will happen? So for this case, the error will happen due to the moving coil current. So here we can, for case A, we can write that the deflection theta is supposed to be proportional to the currents, product of the currents I C and I B. Now we know that IC is actually equal to IV plus I. Let me denote the currents in terms of capital letters. It would be easier to relate with the notation using the figure. So that is for the current through the current coil or the fixed coil. Now the current through the potential coil or the moving coil is actually proportional to the voltage E across the load. So we can further rewrite this proportional relationship as theta being proportional to I plus IV, and instead of IV we can write E. If that is how we are representing the relationship, then if we divide it as EI plus E into IV, then we can say our main focus for determining the power is to concentrate on this particular quantity. So there is some additional quantity in terms of E into IV. So this additional quantity is going to be the source of error if the moving coil is connected after the fixed coils. So as the moving coil current is resulting in the erroneous term, so this sort of error due to the moving coil current is uh, going to result in when the moving coil is connected after the fixed coil. Now another type of error can be accumulating if the moving coil is connected before the fixed coil. So if the moving coil is connected before the fixed coil, then the resultant error would be a result of the fixed coil voltage drop. So again, we can start by writing the proportional relationship between theta and the two currents, that is IC into IV. Now in this case, if the moving coil is connected before the fixed coil, then in this case the current through the fixed coils is going to be same as the load current. However, the voltage across the moving coil will not be same as before. So it would not be equal to E anymore because it is not directly connected across the load. So some voltage drop will take place in the moving coil uh, sorry the fixed coil, and we can denote it as EF, and the total voltage across the moving coil would be the summation of E and EF. So this voltage drop EF that is happening across the fixed coils, in terms of that and in terms of the load voltage, we can say that the uh, current IV can be written or designated to be proportional to E plus EF, because that is the voltage across the moving coil in this case. So this relation can be written as I into E plus EF. Now again, if we separate it into two parts, then this additional term over here is going to be the source of error in this case. And for this type of connection, the source of error is resulted through the potential drop across the fixed coils or the field coils. So to mitigate the possible sources of error, compensated wattmeter configuration can be useful. So here the moving coil connection is done in a different way to mitigate the effect of the source of error. Now if we look at this circuit configuration, then the moving coil is actually connected at this point after the connection of the field coils or the fixed coils, but uh, some additional winding is used along with the connection. So apparently it might seem that the moving coil is connected at this point, but that is not. The moving coil is actually connected after the fixed coils. From that point onwards, another additional set of winding is used which is in the opposite direction of the field coils. So this dotted line over here is representing that particular uh, set of winding that is in opposite direction of the field coils. So that winding is going to carry some amount of current. And what is that current? That is the same current that is supposed to be passing through the moving coil, that is IV. So normally the field coils are kept thick because as they have to carry the load current. So the field coils are uh, done, field coil windings are done using thick wires. But in case of the compensated wattmeters, this extra set of winding or this extra winding shown as the dotted lines is done by thin conductor. So as the purpose is to just to mitigate the uh, source of error, and also this thin winding is not going to carry the load current. It is going to carry the current that is going to pass through the moving coil, and the moving coil normally carries a small amount of current compared to the load current. So thin winding can be sufficient to have the compensated winding. Now the compensated winding has uh, uh, or it is placed right alongside each turn of the field coils, but in the opposite direction. Now this additional winding, as I have already said, is part of the potential coil. Now again, if we try to write the expression of the field coils, now this current that is flowing through the compensated winding will also come into effect, because let's say the flux which is produced by the field coils is due to the current I plus IB. So the fixed coils, they produce flux due to the current I plus IB, which is the fixed coil current or the current coil current. Now this opposing compensated windings is going to carry only the moving coil current, that is IV. So the compensated winding. The compensated winding is only going to carry the current IV. So the compensated winding is also going to develop a magnetic field, and that magnetic field is going to be proportional to IV. Now as the compensated winding is done in the opposite direction, right alongside each turn of the fixed coils, so this magnetic field produced by the compensated winding is going to oppose the main field produced by the fixed coils. So in that sense, we can say that theta should be proportional to E into I plus IP, sorry, I plus IB minus IB. So this negative component is coming from the presence of the compensated winding, as the compensated winding is going to create a magnetic field in the opposite direction. Previously, for this sort of connection, the theta was proportional to E multiplied by I plus B. Now as the compensation winding is producing some opposing magnetic field proportional to IV, now that expression can be modified in this manner. So in that way, it can be said that theta would be more or less proportional to E into I in this case. So as the resultant flux is proportional to I, so in this case, the deflection is also proportional to I. So in this case, the additional source of error in case of this sort of connection, which was this one, This additional source of error is compensated by using the compensating winding, and using this sort of a construction, a better accuracy can be obtained in measuring the power using wattmeter. Now, multi-range wattmeter configuration can be there as well. So where there could be option to select both the different current range or different voltage ranges. So first of all, the current range can be selected by controlling the connections between the field coils. Let's say in this figure, a current range switch has been shown. So a cross-coupled switch has been shown. So if the switch location is changed from one position to another, both the connecting points are going to be shifting together. So now at this point where both the connectors of the switch are connected to 0.5 ampere range, now for this configuration of the connection, the field coils or the fixed coils are connected in series. So the resistances of both the field coils are going to be added up. So the overall resistance of this path will increase. Whereas when the cross-coupled switch is shifted to the left-hand side, or they are connected to this 1 ampere range, then at that configuration, both the field coils are connected in parallel, so their equivalent resistance is also going to decrease. So as the resistance of the path is going to decrease, more current will be drawn by the field coils. Now, to increasing the multiple ranges of voltages, voltage selection range or voltage range switch can be there as well. So where series of resistance can be there, series of multiplier resistors, and depending upon connection of the voltage range switch, at which range it is connected, the corresponding resistance, multiplier resistance will be in effect, and the different amount of uh, 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 voltages across the load can be handled by the wattmeter. So this connection is actually similar to sort of the multiplier resistors used in case of DC voltmeters. So like different multiplier resistors are going to change the amount of current that is going to be carried by the moving coil, and accordingly the voltage range can be changed. Now, if we talk about the using multi-range wattmeters, then let's say you have chosen the current range to be 1 ampere and the voltage range to be 120 volts as per the configuration available possible connections in terms of this configuration. And let's say the scale is calibrated from 0 to 120. Now, if these ranges are selected, 1 ampere and 120 volts, then the corresponding power to these two quantities is 120 watts. So this same scale can be used easily, or directly reading can be taken from this scale to measure the power across a load. Now let's say someone chooses the range of 0.5 amperes for the current range and 120 volts for the voltage range selection. So then the corresponding or equivalent power would be 60 watts. Then reading from this scale, if someone takes reading directly from this scale, that would not be giving the accurate data, because some manipulation has to be done, as the corresponding power to the selected switch is 60 watts, which is half of the full scale deflection available from the scale. So whatever the reading is taken from this particular scale, that should be divided by 2 to get the accurate reading. So in that sense, both the range of current and the range of voltage has to be taken into consideration, what overall power or equivalent power that corresponding ranges are indicating. As per that, the data from the scale has to be manipulated if necessary. Now, linearizing the wattmeter scale. So normally the electrodynamic meter movement mechanism gives non-uniform deflection or non-linear deflection of the pointer. But in case of electrodynamic wattmeters, it is possible to calibrate the scale linearly following some condition, because in this case of configuration, the moving coil and the fixed coils are carrying separate currents. So the moving coil current is proportional to the voltage across the load, and the fixed coil currents are proportional to the current carrying by the loads. So normally what happens that the supply voltage is kept constant, and which means that the voltage across the load is also going to be constant. So the voltage across the load normally remains constant. So if the voltage across the load remains constant, then the current flowing through the moving coil is also supposed to be remaining constant. So due to the variation of the load, I mean, only the current will change in that case, because the voltage is kept fixed. So only one parameter is going to change. So if we recall the relation of theta, which is proportional to E into I, so in this case, E is kept constant because supply voltage is not changed. So as it is constant, so the moving coil current is also supposed to be constant. So overall, the deflection theta then ultimately depends on only one parameter, that is the change in the load current. So in that sense, theta is directly proportional to I, and the scale can be calibrated linearly. So if, for the wattmeters, a linear scale can be constructed like a linear scale shown over here, and that would be easier to take the readings for uh, different types of loads. So with that, I would like to conclude the discussion on electrodynamic wattmeters.